In this lecture, we'll learn about modal analysis of a plate in ANSYS APDL. So the plate I'm going to be modeling in this example is inspired by this video on YouTube. It's called Cymatics by Nigel Stanford, who has shown the effects of cymatic frequencies on matter. And one of the examples he shows on the video is this plate. He's playing the keyboard here and some patterns are showing up on the plate. I want to find the natural frequencies of this plate and see how we can make these patterns on the plate. I don't know the material properties or dimensions of the plate, so I'm going to use fictitious numbers for that. So with that said, let's go to ANSYS and try this example. So if I come to ANSYS and let me open the command prompt so you will see the progress of the simulation. First, I want to define some parameters that I will use throughout the analysis. So the first thing I want to define is a parameter for the length of the plate. I call it PLT underscore length, and I give it, let's say, 7 centimeters. So 7e minus 2. Let me remove the mouse cursor. And then I want to create another parameter called width and give it again 7 centimeters. I'm defining two parameters so that if I wanted to make this a rectangular instead of a square plate, I could change it easily in the script and the model would change accordingly. Now I want to define a radius for the circle at the center of the plate that is attached to the speaker. So I call it src underscore radius, and I give it 5 millimeters. And then I want to define a parameter for the thickness of the plate. Call it PLT underscore THK. And I make it 1 millimeter thick. So 1e minus 3. Now let's define some parameters for the material properties of the plate. So PLT for plate, EX for the Young's modulus, be 49 gigapascals. Similarly, PLT underscore PR for Poisson ratio, let's give it 2.27. And for the density, I just call RO for rho, I give 2500. These values are roughly for an aluminum plate. Now I have to go to pre-processing, so I do \prep7, and I have to define an element type. Before I do that, let's go on this window and see what element types are available for shell analysis. There is 181 and 281, and let's go to the help documentation and see what 281 does. So here we are on the help documentation for shell 281, which as it says in the description, is good for shell structures, basically very thin structures we could model with shell, and we only need to create a an area for that, for example a square or a circle, and we define the thickness of the shell using section type and section data. And then there are degrees of freedom. If you scroll down, maybe we could see that in the documentation. The degrees of freedom are going to be UX, UI, UZ, and rotations. If the key option 1 is equal to 0 by default, but if you convert this into a membrane by changing the key option 1 into 1, basically taking away the bending moments of the plate, we will only have UX, UI, and UZ. We won't have the rotations of the plate. For this scenario, we'll not change the key option 1, so we'll have a shell element. And the material properties we can apply for this element type are Young's modulus, Poisson ratio, a coefficient of thermal expansion, and we can also define density and damping for this element type. So the difference between 281 and 181 is that 281 is a higher order element type. As you can see, it has corner nodes and mid nodes. But if I find element type 181, which is here, if I scroll down, I see that this is a lower order shell element which only has one node at the corner, at each corner, so it doesn't have mid nodes. For this example, I'm going to use element type 281. So I see 80, reference number 1, and the value is 281. And I'm not going to change the key option 1 as I said before. I don't need to apply a real constant, so I go directly to material properties. MP for material property, EX for Young's modulus, 1 the material model, and PLT underscore EX was the value I was giving for the Young's modulus. So if I click enter, it goes there. And I can now change the Poisson ratio by just pressing the up button and going back to my command history. So PRXY. Now I want to give the density. So I said rho, and this one would be density. So if I come to material models, you can see that, oh, actually here, density is given, and also the linear elastic material property is also given there. Now I want to define the section type. So if I type section type, reference number 1, and shell for the section type, and again, section type shell does not have any subtypes, so I can just press enter here. And if I give section data and give the values, so the first value for section type shell is the thickness, which we said was PLT underscore THK. The second one is the material model. I give 1. And next is orientation. By default is 0. Also, we have a linear elastic isotropic material, so it wouldn't really matter, but just give 0. And the next one is the number of divisions. I can give just 5 or 3, but so let's just leave it at 5. So I also have the section type defined for me. So if I come to sections, go to shell and layups and plot section, there's one section type defined for this shell element. It's now time to create the key points for this analysis. So I define a key point. I leave this number empty, so ANSYS will pick the most appropriate number. And first I create a key point at the center of the coordinate system. So 0, 0, 0, which is right there. Now I want to create the key points for the circle, so I can create an arc. So I could say key point, next one is at SRC rad for X, 0, 0 for Y and Z. So that one is here. I can create another one. This time I move in Y by the radius of circle, but don't give any values for X. So it becomes this key point. So I can create an arc there. Next, I want to create the points for the plate, the corners of the plate. So I create a key point at, let me move this a little bit further, PLT len 0, 0. So now key point 4 is created there. Next key point I want to create at this location, PLT width, which is again I've defined earlier up there. So it is created there. And the last key point is going to be 0, PLT width 0. So I have all the key points defined for the plate model. Now I have to create lines with these key points. And the first line I want to create is between key point 1 and key point 2. So I say L1, 2. Then I want to create a key point between lines 1 and, or a line between key points 1 and 3. So I say L1, 3. Now I want to create a line between, or an arc between key points 2 and 3. So I say L arc from key point 2 to key point 3. The center key point is 1, and the radius is CRC rad. So that radius, or that arc, is also created. Now I want to create a key point or a line between key points 2 and 4. Also want to create a line between key points 6 and 3, and between 4 and 5, and 5 and 6. So I say line between 2 and 4, line between 4 and 5, line between 5 and 6, and line between 6 and 3. So all the lines are created. The next thing I want to do is to do line divisions. I want to divide the lines here 1, 2, 3. So if I do \pnum line 1 and do lplot, so now line numbers are shown for me. Lines 1, 2, 3, I want to divide them by 8 divisions. So I say lcell S for selection, and now I want to say line from 1 to 3. If I do lplot, only those lines are selected, and I can say le size all, and then put 3 commas and say 8. Now these are divided by 8 divisions. I do all cell to select everything, and lplot. Now I have to divide the other lines. I want to divide lines 4 and 7 by 60 divisions. So I say lcell S lines 4 to 7 at every 3 increments. I see that only lines 4 and 7 are selected. I do le size all and give 60 for the number of divisions. Do all cell, and I did this to have a fine mesh for the analysis. So if I do lplot now the only thing I have to do is to divide lines 5 and 6 by a number of divisions. So I say lcell S line 5 and 6, and I want to divide them by 40 segments. So I say le size all 3 commas 40. Next I have to create areas with the lines that I have already created. So first let me do all cell, and say AL areas with line, and pick the first 3 lines 1, 2, 3. So that area is created. Now I want to create an area with the other lines. So I say AL with line 3, 4, 5, 6, and 7. So the other area is created. In order to be able to do mapped meshing, I want to merge lines 5 and 6 so that it maps to line 3. So I say LCCAT, which means merge 2 lines, and the lines are 5 and 6. So if I do that, lines 5 and 6 are now one line, line 8. Now it's time to mesh my areas. They're all the same element type and the same material model. So I can say type 1, mat 1, and also section type 1, which was the shell. Now a mesh all. And here I don't need to define e size because I have defined the line divisions for all the lines. So if I do a mesh, see that a mapped mesh is created for this model. Now the next thing I want to do is to define the symmetry boundary condition. So this is a quarter symmetry. I want to apply symmetry here and symmetry here. So the first thing I do is select lines at y equals 0, or nodes at that location. I say n cell S by location at y equals 0. If I do n plot, you see that only all those nodes are selected, and I can say D for degree of freedom for all these nodes, UI is 0. Now I can do all cell and eplot. Now I want to select the nodes at x equals 0. So I say n cell s location x equals 0. Now those nodes are selected. I could say D all, now ux equals 0. All cell eplot. Now what I want to do is to select a boundary condition for the nodes at the circle, which is the one that moves up and down with the speaker. So what I want to do here is that I want to restrict their motion in z direction, basically perpendicular to the plane of this model. There are two ways to do this. One is to select the area, which was area 1, and then select the nodes attached to it. Or the other one is to change the coordinate system to cylindrical and then apply all the nodes in a certain x, which would be in the radius of the circle, and apply the boundary conditions there. So let's do the second approach. I do csys, comma 1, and let's take a look at the help documentation about what csys is. If I come to the commands and find C and find csys. So csys activates a previously defined coordinate system, and if I give 0, by default would be Cartesian, but if I change it to 1 as I did, it would change it into a cylindrical coordinate system with Cartesian z as the axis of rotation. Then you can have 2 as spherical, and on and on. And if you want to create your own custom coordinate system, you can start by numbering them at 11 as the minimum coordinate number, and then go on create other coordinate systems. So I picked it at 1, which is cylindrical coordinate system. Now I want to say n cell s location x of that location from 0 to src rad, or crc rad, which as we defined up in the script up here was the radius of the circle. So I'm saying select all the nodes at this x, but because I'm in the cylindrical coordinate system, it's going to be a radial coordinate. So if I do that and say and plot, so all these nodes which are in the cylindrical coordinate system of this radius are selected. Now I'm going to say D for all these nodes, all the degrees of freedom are equal to 0. Now I do all cell and eplot, and before I move on, I change the coordinate system back to Cartesian. csys 0, so I'm back to Cartesian coordinate system, and finish the pre-processing. Now I'm ready to apply the modal analysis features. So before I type the code, let me just show you how you do it on the window. If you come to solution, analysis type, new analysis, the second one says modal. If you click there, then you can come to analysis options and define the properties of the analysis. So modal option, M-O-D-O-P-T, you can pick several extraction or mode extraction methods. For this case, we will go with the block Lang-Sauce, which is by default for simple analysis like ours. But if we had coupled physics or we have damped physics, we had to use either of these. Then we have to define the number of modes to extract, and then in mexpand command we could define mode shape expansion and number of modes. Also, do we want to calculate element results like stresses or strains in this analysis? And the commands in MAPDL help documentation are found here. So if I find MODOPT, so MODOPT, let me move it here. If I can't keep them in the same place. So MODOPT requires the method and the number of modes, initial and ending frequency, which we could leave blank so it would be unlimited, and then complex mode if we want for a complex mode analysis, which is defined in here. We could say on to calculate complex eigenshapes, or off to not calculate complex eigenshapes. And then mexpand, which is here, number of modes, frequency start, frequency end, and eCalc element calculations or not. So let's give the values as we wish. So let's go to solution and say n type, modal for modal analysis, MODOPT, lamp for the lamp block length source. So, and the number of modes that we want to extract is 15. I don't want to have an initial frequency or ending frequency, and complex mode, let's say on. Next, I want to define the mexpand. So mexpand, number of modes again 15, no initial frequency, no ending frequency, and eCalc, yes. And here it is. We are ready to solve for the modal analysis or natural frequencies of this plate. So if I say solve, it's going to be solving. It's going to take a short while, and we can see the progress of the simulation here. So it did the simulation, completed. It's doing the expansion right now, and solution is done. Now I can finish solution, come to post 1 and say set comma list to show me the natural frequencies. So I got the first 15 natural frequencies of my plate based on the material properties and the dimensions that I gave. Now let's show the 8th mode or 8th mode shape of this plate. You can say set to read a certain natural frequency. Or before I do that, let me show you where I can find these from. If I come to general mode, general post processing, come to read results by pick. These are the list of natural frequencies that are calculated for this analysis. So the 8th one is here, and as you can see, the command is set. So it says load step 1 and sub step 8. So this is just one load step, and there was 15 sub steps for it. So if I come here and say set comma load step 1 and sub step 8, so that one is read into the database, and I can say pln sol plot nodal solution u for displacement and sum, and this would be the displacements of the plate at its 8th natural frequency. And we can see that here. The numbers are not accurate because this is a mode shape, and this is for natural frequency where the displacements are going to be high, but we haven't applied any forces here, so it's just a demonstration of the displacement of this plate, which is similar to the shape that we saw in the video. And this is a quarter symmetry, so if I come here, go to styles, symmetry expansion, periodic, and do 1/4 and apply. And if I can zoom, see the mode shapes or mode shape of this plate at the 8th natural frequency. So in this video, we'll learn how to define or how to do modal analysis and set the appropriate features of a simple modal analysis for a plate and vibration.